Hey guys, I'm going to use the parallel axis theorem to figure out what the moment of inertia is for a hula hoop, and then we're going to use the second law to derive what the period would be if we allowed it to oscillate back and forth. And this will go along with our parallel axis theorem lab. And then we'll finally test to see what the period actually is of the hula hoop. All right, so I'm going to start with what my moment of inertia would be just for a hula hoop. And if I had a hula hoop, I could say that it is very thin and all of the mass is located a certain distance away from the center. And so it would be equal to mr squared, which is what our moment of inertia is for a hoop or a thin disc. All right, so the parallel axis theorem. Morning.
I want to change your clock.
Oh. All right, so this would be if I have my hula hoop and I'm saying that the axis is in the center. What I'm going to do is I'm going to move it a distance up here, which is known as D. And I'm going to change my axis from the center to the edge. So the parallel axis theorem tells us that this is going to be equal to our initial moment of inertia plus m times d squared. And it turns out that in this case, d is r, because it's the radius. And so this is going to be mr squared plus mr squared, or 2mr squared. All right, so when I displace this a certain distance and let it swing back, the restoring force, our force that's trying to get it to go back to equilibrium, is a component of the weight. And this component of the weight is related to the angle theta that I am displacing it. So it's going to turn out that our restoring force is going to be negative mg sine of theta. Now the center of mass of a hula hoop is going to be in the center. So this is going to be where our center of mass is. And so I can say that the torque that's trying to rotate this is going to be equal to this force times the radius, and that's going to be equal to our second law in rotational form. All right, so for these problems, if you remember, we have to make some assumptions, and our assumption is that it's going to be for small angles. So it turns out that for small angles, that sine of theta is the same as theta. So I make a theta substitution for a sine of theta, and that's going to mean that when I have this going back and forth, theta is going to be small for the most part. So I'm not going to displace it all the way from the side and let it go like that. And in doing this, I'm saying that most of the motion is in the x direction and not in the y direction. And again, maybe I should write the second law in its so the sum of our torques is equal to the cross product of the radius times the force. which is equal to I alpha. All right, so with this substitution, I have negative mg theta r is equal to I alpha. And we said that I is 2mr squared. So I have negative mg theta r is equal to 2mr squared alpha. And I'm going to be able to cancel some things out. Why don't I get rid of an m and get rid of one r? All right, now the other substitution that we know is that we can say that this is related to a cosine omega t. And again, this omega is our angular frequency, not our angular velocity. And I know that the second derivative of theta with respect to time is going to be our angular acceleration. So if I take the first derivative of this, I get that it's minus a omega sine omega t. And then my second derivative, which we're saying is alpha, is going to be equal to negative a omega squared cosine omega t. All right, so I'm going to substitute this in for theta and this in for alpha. And I'm going to get minus g a cosine omega t. And then I have 2r negative a omega squared cosine omega t. And the nice thing here is that our cosine omega t goes away. And we're left with our negative a goes away. We're left with that g is equal to 2r omega squared. Now, if you remember this omega, this angular frequency, or if you look on your equation sheet, we know that omega is going to be equal to 2 pi over the period. So I'm going to plug this in because I want to get an equation for the period of what this is, and then we're going to test it. So I get that g equals 2 pi. This is going to be 2 pi over t squared. And so I have g equals 2r 2 pi squared over t squared. And so I have t squared is 2r over g times 2 pi squared. And so t is going to be equal to 2 pi square root of 2r over g. So 2r ends up being the diameter of this. And so I'm going to measure this, and then we'll calculate it. And it looks like it is, I have 86 centimeters. So 0.86 meters. And so t is going to be equal to, because it's not really convenient to measure the radius, right? It's a lot easier to measure just what the diameter is. And so I'm going to grab a calculator, and then we'll test it. So I have 2 times pi times the square root of 0.86 divided by 10. And I got 1.8 seconds for my period. All right, I'm back, and we're going to time this. And again, instead of timing this one time, because just the hand error could be a tenth of a second, a little bit more than a tenth of a second, I'm going to time for 10 periods and then divide by 10. All right, so I'm going to displace it a short amount. And again, a period is going to be the whole path, and I'll time it for 10. So I'm going to displace it and start it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I got 19 seconds, which we said it was 1.8 seconds. It was actually 1.84 seconds. So I feel like that's pretty close. All right, I'm going to show you something else interesting about the period of a hula hoop. Okay, so welcome back. It turns out that the period of the hula hoop, which we found to be 2 pi the square root of 2r over g, is also the same as the period of a pendulum that has the same length as the diameter of the hula hoop, because 2r would be the same as L. And so behind here I have a pool ball, and I have it to be the same length as this, and we're going to find out that when I displace these and let them go, they should have the same period for a small angle displacement when they go back. So that's an interesting side note for these.